Hello everyone, my name is Ayub and I am honored to represent the fourth group in this cybersecurity project for cybersecurity fundamentals with Professor Qutaiba. Our particular project concerns pseudo-random number generation and its implication in implementing security softwares. This project was obtained as part of an open lab assignment from Seed Labs. So when we say random numbers, what do we really mean by that? In the realm of computer science, random numbers are essentially a sequence of bits generated in a manner that ensures each number in the sequence is independent of the other and avoid following any predictable patterns. Random numbers serves as a fundamental component in a wide range of applications, like gaming, statistical sampling, and cryptography. To be more specific, a random number is a number chosen by chance, in other words, randomly from a set of numbers. All the numbers in a specified distribution have equal probability of being chosen randomly. Random numbers are used in security a lot. Here are some examples. Algorithms. Random numbers are used in algorithm that needs a key to be generated. For example, AES algorithm. We used random numbers to generate these keys. Also, salts. Salts are a string of characters that attaches to a password to defeat rainbow tables. Nonces. Nonces are number used once. We use this in a challenge response mechanism or protocol. After defining what does pseudo-random means, this brings us to our lab today. This lab consists of 5 major tasks that shall gradually demonstrate how we go from generating pseudo-random numbers using software-only resources versus a more particular approach that involves hardware inputs as well. We hope to shed some light on how computers approach randomness and how that relates to writing sound security software. In the first task in this project, we will try to generate a 128-bit random stream using this program. So essentially what is going on here, that we utilize a random function provided by the C standard library to generate a random bit number between 0 and 255, and then cast it into a hexadecimal character representing the character code range. But when we say seed, what does that mean? A seed value is the starting value that is used to determine how the final result will look like. So let us run this program multiple times and see how the output will look like. After running the program for 3 times, we can observe clearly that each time the program generates a completely different key. But what if we comment this line and see how will the key look like? After running the program multiple times without passing the argument time null to our function, we can observe that the key is exactly the same. Why is that? This is simply because we didn't pass an initial seed to our function.
Imagine that a CEO of a big company has encrypted a very valuable file using a key generated by a program in task 1, and a hacker has managed to steal this encrypted file from the CEO's machine and noticed that it was encrypted using AES 128 CBC.
The hacker stole the encrypted file and knew some information about it. The file was encrypted using AES algorithm and a key generated from task 1 program. Though the file is encrypted, there are some data that cannot be hidden. For example, the timestamp, which is basically when was the file created. Also the plain text, which is the first 16 bytes of the file. The attacker knows that the file is a PDF file. PDF files has a common version used, which is PDF 1.5, so the first 16 bytes are predictable. Next, obviously the ciphertext, because he stole an encrypted file. Last thing, which is the initial vector. The initial vector is basically a pseudo-random number that ensures that no two plain text have the same ciphertext. After having all of this valuable data, there is one assumption left, which is when the file was encrypted. The attacker in our case assumed that the file was encrypted in a time window of 2 hours. So 1 hour before the original timestamp and 1 hour after the original timestamp. 1 hour is basically 3600 seconds. So simply the attacker will have to do a couple of steps. First, generate a key for each timestamp in this time window. We use generate float key. And then we decrypt the ciphertext given and compare it to the plain text. After generating the key, we will try to decrypt the ciphertext using the key and compare it to the plain text. Now simply we compare the decrypted text with the plain text. If they match, then we found the key. Let us run this program and see what happens. What is happening here is simply that the program is brute forcing all the possible keys that might be used to encrypt the file. And here we find the key. In this task, we are measuring the entropy of the kernel using this command, as we can see. So we can see that the entropy is increasing. This is because we are using the mouse. We are moving the mouse and pressing on the keyboard. And these are hardware. We will also consume this entropy using the div random. The div random has a feature, or it might not be a feature, which is blocking. If there is no entropy inside the kernel, the div random will block and wait until it reaches a certain level and then generate a random number. Although this can be considered more safe, it can cause denial of service attacks. Also, we can notice when we are surfing the web, the entropy increases, but not as much as when we move the mouse or press on the keyboard. This is because the randomness in moving the mouse is a lot higher than DNS lookup, for example. In this task, we will do mainly 3 things: using urandom instead of random, outputting a 1 megabit file using urandom to check its quality, and generating a 256-bit encryption key using a C program. So let us watch the entropy, and then let us use the div urandom to see how the entropy behaves. So when we run it, entropy increases. This is because the current generation of entropy is higher than the consumption, because one of the hardware resources that the kernel implements is actually the disk interrupts. Now we are going to test the quality of urandom by outputting the bit stream into output.bin. As we can see, the random says 127.5, and this is nearly the max. The max is 128. This means that the quality is very high. After seeing the quality of urandom bit stream, the question asks itself, do we really need div random? Since the quality of div urandom is not actually bad, we can generate an encryption key using the div urandom. So here is a program that generates a 256-bit encryption key. As we can see here, it generates a 64 hexadecimal, which is actually 32 bytes.